Hello, my name is Gabriel Silva, and I'm gonna present my current work called Biogenicity Influences in Iron 2 Bearing Minerals by extremely acidophilic bacterium Acetobacillus furoxidans. This work was developed in the Chemistry Laboratory at the Chemistry Institute of the University of São Paulo, Brazil. So, let's begin. In this work, we used the microorganism Acetobacillus furoxidans, a chemolithotrophic bacterium that is able to gain energy from the oxidation of inorganic substances. In this case, it can use the oxidation of iron and sulfur. And the energy produced is used to fix carbon dioxide for the production of biomass. All of this can happen in a very acidic environments, with a pH as low as 1.8. We choose to use two minerals in this study, siderite and vivianite. Siderite is an iron carbonate. It can be used as a source of energy to the presence of iron 2 ion, and carbonate that can be used as a source of carbon for biomass production for the microorganism. This mineral was already confirmed on Mars. Vivianite is an iron phosphate. It can be used as a source of energy for the microorganism and is also a source of phosphorus. Among the main elements used by life, phosphorus is the less common both on Mars and on Earth. The presence of this mineral was not confirmed on Mars, but it's possible that it can be found on phosphorus-rich patches found on the planet. On Earth, both minerals can be found associated with life. For example, both minerals are already found in different kinds of fossils. After the microorganism grows, we look for signals of the bacterial activity in the minerals. To differentiate physical and chemical alterations from biological modifications, we use the biogenicity criteria to identify the so-called biosignatures. Those biosignatures can be mechanical, like the disruption of the mineral grains, or biochemical. These include productions of nanocoatings from, for example, deposition of EPS, extracellular polymeric substance, that, after drying, can form desiccation cracks. Other biochemical signatures include microtopographic changes, like pitting, itching, and formation of paths by moving cells, enhanced dissolution of the minerals and production or precipitation of secondary minerals. The study of possible biosignatures in rocks and minerals in a Martian context is recent. A very important work published in 2021 used a thermoacidophilic organism called Metallosphera cedula, growing over a Martian meteorite, but focused on the formation of intracellular biomineralization and other molecular biosignatures. Our work started with the first investigation of the growth of Acetobacillus furoxidans on siderite and vivianite. The very first results of this work were present in the last AbGradCon by our colleague Roberto Vicenzi, and now the manuscript is in the last stages of preparation. So, what is our goal in this work? In this study, we evaluated different biogenicity criteria as biomechanical and biochemical changes of biosignatures on the minerals siderite and vivianite exposed to an acidic medium in different conditions as abiotic and biotic with the presence of the microorganism Acetobacillus furoxidans. To do so, we use the following. In the cultures, we use the LR strain of the Acetobacillus furoxidans, growing the modified T and K medium with the addition of the mineral as the only source of energy for the organism. The cultures were made in two conditions, biotic and abiotic, as a control, always in a pH of about 1.8 at 30 degrees in an incubator shaker table at 180 rpm. For each culture, it was added about 5 millimole of comminuted and shifted siderite or vivianite. The analytical methods employed to study the minerals were SIM, scanning electron microscopy, IDS, energy dispersive X-ray spectroscopy, Raman, and XRD, the X-ray diffraction. So, these are the results we obtained. First, the siderite. On the left, one can see an SIM image of a typical grain of the mineral before the experiment. A large piece is covered by smaller and sharper grains broken during the mineral grinding. Unfortunately, the siderite was almost completely dissolved in the abiotic assay. However, on the right, one can see the result of the biotic assay. On the first picture, we can see a formation of paths left by the cells. They have a richer signature in carbon, shown in red, probably by the position of the EPS. The second picture, one can see the desiccated EPS forming contraction cracks. The mineral is under the EPS and can be recognized by the presence of magnesium, shown in yellow. Over the EPS are amorphous grains, probably schwarzmannite, a bioprecipitate formed from the iron 3 produced by the microorganism. The last picture gives a better perspective of the desiccated EPS covering a siderite grain. The vivianite shows a similar pattern. In this case, we have on the left the result of the abiotic attack on the vivianite. Again, one can see sharp pieces of mineral, while on the right, the biotic experiments produced EPS-curved grains with contraction cracks. Once again, it was found round amorphous minerals covering the vivianite. However, this time their composition wasn't compatible with the mineral schwarzmannite. Using Raman, we compared our pure vivianite, marked as V, with the vivianite left after the abiotic and the biotic experiments, respectively marked as VA and VB. We also used data from the literature for metavivianite, a natural slightly oxidized vivianite phase, whose peaks are marked as MV, and pure vivianite, marked as V star. We also collected data for Santa Barbarite, an amorphous iron 3 phosphate considered a completely oxidized phase of the vivianite. Our initial vivianite shows some peaks of both vivianite and metavivianite, but both biotic and abiotic showed some decrease of amorphous phases, similar to the Santa Barbarite. To better evaluate the hypothesis of the formation of a Santa Barbarite in the cultures, we made a XRD with our pure vivianite, a pure sample of Santa Barbarite, and the material left after the abiotic and biotic cultures. The graphic A shows again that our initial material is a mixture of vivianite with metavivianite. The graphic B shows a highly amorphous Santa Barbarite. The graphic C shows some degree of amorphism, but the vivianite peaks are strong and easily identifiable in the abiotic sample. However, the graphic D, the biotic sample, is highly amorphous, show a good similarity to the Santa Barbarite, corroborating with the idea that the microorganism induced the formation of Santa Barbarite as the bioprecipitation, instead of the schwarzmannite. So, to conclude, first, we were able to identify many biogenic criteria in our mineral samples to be used as biosignatures of the growth of the Acetobacillus fluoxetans. These biosignatures can be used while looking for outlife signals both on Mars and on Earth. Also, we have strong evidence of the production of Santa Barbarite, a biomineral that, unlike schwarzmannite, was never described for cultures of Acetobacillus fluoxetans. These and other discoveries will be included in other manuscripts that is also in preparation. Open questions and future work. This work opens paths for more questions that could be addressed. Are there other biogenic mineral phases that could be found on Mars? What other minerals can be a source of iron 2 for microorganisms like Acetobacillus fluoxetans in a Martian context? How these biosignatures could be affected in a more complex context, like in the presence of brines on the ancient Mars. Also, to complete this work, we need to find the definitive identification of the phosphor-bearing amorphous mineral phase found in the biotic cultures of vivianite. Is it really Santa Barbarite? We also want to do more research to better understand the development of biosignatures of iron 2 bearing minerals mixed with different kinds of sediments. And last, we need more research of the biosignatures of iron 2 bearing rocks as models of Martian lithologies, like for example the use of more complex rocks like basalt. To finish, I'd like to thank all the collaborators and colleagues that helped in this study, and the agencies that contributed to have the work done. Please, feel free to contact me with questions and suggestions. Thank you very much for your attention.